Python, simultaneous pseudo-inversion of many 3 by 3 singular, symmetric matrices. I have a 3D image with dimensions rows x calls x steps. For every voxel in the image, I have computed a 3 by 3 real symmetric matrix. They are stored in the array D, which therefore has shape, rows, calls, depths, 6. D stores the 6 unique elements of the 3 by 3 symmetric matrix for every voxel in my image. I need to find the more Penrose pseudo-inverse of all row call steps matrices, simultaneously / in vectorized code. Looping through every image voxel and inverting is far too slow in Python. Some of these 3 by 3 symmetric matrices are non-singular, and I can find their inverses in vectorized code, using the analytical formula for the true inverse of a non-singular 3 by 3 symmetric matrix, and I've done that. However, for those matrices that are singular, and there are sure to be some, I need the more Penrose pseudo-inverse. I could derive an analytical formula for the NP of a real, singular, symmetric 3 by 3 matrix, but it's a really nasty / lengthy formula, and would therefore involve a very large number of, element-wise, matrix arithmetic, and quite a bit of confusing looking code. Hence, I would like to know if there is a way to simultaneously find the NP pseudo-inverse for all these matrices at once numerically. Is there a way to do this? Gratefully, GF.
NumPy 1.8 included linear algebraic funcs, which do exactly what you are after. While np.lineage.pin does not funced, np.lineage.svd is, and behind the scenes that is the function that gets called. So you can define your own goopin function, based on the source code of the original function, as follows. And you can now do things like and of course the results are correct, both for singular and non-singular matrices. And for this example, with 50 times 40 times 30 equals 60,000 pseudo-inverses calculated. Which is really not that bad, although it is noticeably 4x slower than simply calling np.lineage.inv, but this of course fails to properly handle the singular arrays.
Edit, see at Jamie's answer. Only the discussion in the comments to this answer is useful now, and only for the specific problem at hand. You can do this matrix by matrix, using SciPy, that provides pin, link, to calculate the more Penrose pseudo-inverse. An example follows. This does not exploit the fact that the matrix is symmetric though. You may also want to try the version of pin exposed by NumPy, that is supposedly faster, and different. See this post.